This video presents the joint voice activity detection and audio anonymization component developed by Odering and FPK during the Marvel project. This video extends the demo presented during the first review, in particular for what concerns the advancements for the audio anonymization part. The joint component was developed under two work packages. WP3, in particular task 3.1, AI-based methods for audiovisual data privacy, for what concerns the anonymization part. And W4, task 4.2, device platform for audiovisual analysis and anonymization for the voice activity detection component. The goal of the component is to protect the privacy of the citizens being recorded by the microphones of the Marvel platform by removing from the audio signals any information about the identity of the speaker, while preserving the acoustic surrounding environment as well as the speech content. In this way, the other AI component can process the audio signals in a transparent way. The requirement for the component is that it is deployed as close as possible to the acoustic sources, which means close to the microphones on the edge devices. In this way, the audio signals can be transferred through the edge fog cloud infrastructure without risks for the citizen privacy. These constraints introduces limitations on the computational complexity and memory footprint of the component, since edge devices are typically characterized by very limited computational resources and memory. The component is part of the security, privacy, and data protection subsystem. It provides anonymized streams to the models deployed on the edge fog or cloud tier, as well as inference results to the related data instances for what concerns the voice activity detection. The component deployed in the prototype, therefore, consists of two blocks. The voice activity detection, developed by Odering, is based on lightweight LSTM models, and its goal is to detect speech segments to be anonymized in the audio stream captured by the microphones. In the anonymization component, which is based on signal processing manipulations of the recorded audio, for example, like format shifting, pitch randomization, and randomized frequency shaping. The code of the component is based on the parse and mouth library. The overall component, via voice detection plus audio anonymization, can take as input the audio signals directly from the IFAC MEMS microphones or from any other audio stream, and it provides as output the speech boundaries via MQTT messages and anonymized streams. In the picture, you can see a sample of the audio device deployed in the Trento use cases, where you see the red board are the MEMS microphones, and the green board is the Raspberry Pi, where all the processing runs. Within the prototype, the component is deployed on edge devices, as mentioned before. So on Raspberry Pi, in the UNS and MT use cases, or on Linux workstations in the Green Road use case. The component connects to the MQTT broker, and to which it sends messages with speech boundaries. And it provides the anonymized streams to an RTSP server, which is typically deployed on the fog or on the edge tiers, depending on the use cases. And in turn, this RTSP server makes the signals available to the other components. In particular, during the second part of the project, we developed also more advanced approaches based on neural networks. One solution is based on a sequence-to-sequence approach, which rely on pre-trained speech embeddings, for example, from WaveLM, while the final neural solution is based on S3-PRL, self-supervised speech pre-training and representation learning toolkit, in combination with a speaker disentanglement approach applied during training and developed in particular for the project. These latter methods considerably improve the identification of the speaker while preserving the speech quality, as shown in the table. However, its computational complexity did not allow deploying it on the edge nodes, so in the final prototype, we have the signal processing-based method. We now show some examples of the voice conversion approach applied for the audio anonymization. We consider cross-talking signal taken from the LibreSpeech dataset. So the first is the original signal.
Her eyes seem to regard him with mild pity. Her hope.
Then we have the conversion obtained using the signal processing approach.
Her eyes seem to regard him with mild pity. Her hope.
And then finally, the neural approach, which considerably keeps the prosody of the original signal.
Her eyes seem to regard him with mild pity. Her hope.
Now, to conclude, we show also a short video displaying the voice activity component in action using an offline version, not the real-time version deployed in the prototype. The voice detection in this video processes speech signals interleaved with music and poses.